There isn't anything wrong with Paul Falstad's simulator or the cell phone version, Proto something or other. I tried out yesterday. I put it through its paces. I gave it Eric Dollar's analog computer in LMD mode, longitudinal magnetodielectric modality, and I gave it 3 daisy chain modules, interconnected magnetically, not electrically, with each other. I gave it the maximum size of inductance on those transformers of 100 henries on each coil, and maximum capacitance within each module, within the pair of capacitors within each module of 10 farads that the simulator allowed me to go to. And then I put resistances in between all of the components to try to make things more interesting. And I started with 1 ohm resistance. And then I took it to the max of 1 gigaohm of resistance for each resistor. And then over on one side, I terminated the daisy chain with, instead of going to 2 capacitors, I went through a lamp. And then on the other side, the so-called input side, I also put a lamp, but in parallel to it, I put a switch and a sine wave generator, which I replaced with a battery. And I gave both of them the minimum, in each case, I replaced either one with the other. I didn't have both at the same time. I gave them the minimum voltage of, I think it's 1 millivolt he allows. And the frequency, when it was the AC, I just left it alone. It was 40 cycles per second. I knew, there were all these little hints that told me that, oh yeah, this is a knockoff of Paul Falstad. Even though he may not have created the cell phone app, it's the way the layout is, everything about it. Anyway, so I did that, and I didn't even have to throw the switch. The presence of the voltage source alone, in an open sub-circuit branch of the circuit, was enough to get the circuit going. And the odd part was when I went to the lowest time interval of 1 picosecond, then the thing just explodes. Even despite the 1 gigaohm of resistances throughout the circuit. Now, when I had it at 1 ohm of resistance, I didn't have to go that low in time interval to get explosive results. All I had to do was go below 1 microsecond. So anything less than 1 microsecond, 999 nanoseconds. And this is the same deal in Paul Falstad's simulator. If you go below 1 microsecond, because his standard is to start you off at 5 microseconds. And yet, if you go below 1 microsecond, you get explosive results just based on the time interval alone. Now, he'll call it round-off error, I'm sure, even though he said in his discussion on GitHub, I opened up a question that his JavaScript version for the desktop computer, not for the cell phone, but for the desktop computer, is 64-bit enumeration of the various values of the parameters that are being calculated. And you cannot get round-off error with 64-bit registers. It's impossible. It is so nearly impossible that it is impossible. It cannot happen. And yet I saw recently a posting, somebody asked a question about some circuit, and he said, oh, that's round-off error. It's impossible. It can't be done. Since Windows 10 came out with 64-bit register usage, it cannot be done. So, what is going on? If it's impossible, if he's given the wrong answer as to why it's impossible to get round-off error, then what's going on? And I figured it out. This has been kind of bugging me because he's got a lot of buggy issues. And you know why he has? Before I answer the question, it's because he's so idealistic. He has created a simulator that is so perfect to what he has been taught. He has not allowed anyone's agenda to get in the way. And so initially when he would say, when I would raise questions, he'd say, well, that's weird. That's something wrong with the simulator. That was back in 2017 when I raised the issue. I sent him a circuit based on one of his circuits. It's on his web. He has a web page for each one of his circuits, and the web page is Transformers with DC. Transformer W/DC. And in that, he says, oh, initially the transformer passes DC, but eventually it stops. It can't pass it anymore. Well, I got it to pass continually. And again, with a battery, with a switch, and the switch is kept open, and yet the thing explodes slowly, not immediately, with a hyperbolic exponential growth rate. And I sent it to him. That was 7 years ago. I sent it to him, and I called it, Is This Realistic? And I even made the shortcut in tinyurl.com, Is This Realistic? And I I had different numbers because I came up with different variations. Is this realistic? 1, 2, 3. Well, no, I never number the first one because I never expect to do multiples. But then from afterward that, I start off numbering 2, 3, 4, 5, 6, at the end of Is This Realistic? And I put hyphens in between the words. And he said, no, that's weird. There's something wrong with the simulator. But it's because he's so idealistic. Now, Spice goes to a lot of trouble not to be idealistic, to try to be more like the real world. Well, their version of the real world ain't logical. It's flawed in its own way by being contrived. For instance, Spice presumes all your coils are going to be wound out of copper enameled magnetic wire. Well, what about aluminum? What about iron? Iron floral wire is insulated, and you can get insulated aluminum wire. Totally different magnetic properties to the material of construction for that coil. And it'll make a difference in the behavior of the dynamics of the electricity going through that coil. Well, Paul Falstad doesn't go there, but Spice does. Spice restricts you to copper coils. And then you got to throw massive voltage at it if you test it with Eric Dollard's analog computer in LMD mode, such as I did. And I wrote a piece and I put it in a PDF on my website, but I also put it, I believe, on Quora, called The Perfect Circuit. And I even published it on Amazon, The Perfect Circuit, I believe. Yeah, that's right. Because I got it to work. But all you get are spikes, these voltage spikes with hardly any current, because you can't get any current out of it because you're dealing with models, software models that are modeling copper wired coils. And so all you're going to get are voltage spikes. You're not going to get nice wavy waveforms like you do in Paul Falstad's simulator, because he does not presume that. He doesn't presume anything except the perfect, purely perfect DC transformer, AC transformer, call it what you like. But it does not lose its magnetic field, unlike what Oliver Heaviside had to deal with in the 1880s with the telegraph cable transatlantic problem, because it was purely copper. And he said, hey, you got to put some iron in there, one way or another, and they did. And up until 1956, they never changed their solution until they changed it and took out the iron and put in repeaters across the oceanic bottom, the floor of the Atlantic Ocean. But up till then, they used permalloy tapes wrapped around the copper cable, solid core copper cable, and then put on a very thick layer of insulation, very thick, That was not what Oliver Heaviside had suggested. Specifically, he suggested iron filings in the insulation, but their permalloy idea worked mighty fine, so that was how they solved it for many a year, for many a decade. So we literally, and then to this day, you find motors, they're wound with copper wire, all these Tesla motors, woohoo, and so we got to give it 300-400 volts and wonder why. Nathan Stubblefield never had to do that. He planted his coil underneath the roots of an old oak tree because he had bare iron wire mixed in kind of a bifilar winding with his insulated copper wire, insulated with a cotton sleeve, and he never said in his patent that he coated the cotton sleeve with a goop, an insulative goop, but back in his day, they were using what Tesla also knew about: carnauba wax, pine rosin, beeswax. It was a standard recipe back then. You look it up in any old handbook and you'll see that it's there. They just had each person had their own version. Tesla had his version, 5% carnauba wax, and the remaining 95% was split 50-50 between pine rosin and beeswax. But there were all kinds of recipes because it behaves like a dielectric as well as an electret. Both. Nowadays, you can use Teflon to get the same results, or another substance called Delrin, Delrin, which Delrin was, and Teflon, both were used in the E.V. Gray motor of the 1970s that Richard Hackenberger had been working on. Not Marvin Cole. We don't know about Marvin Cole's version that levitated. We only know about Richard Hackenberger that was tested by the Bing Crosby Foundation as putting out something like 290 times more energy than it took to run it. They had so much energy, they didn't know what to do with it. And he didn't have a AM radio nearby to warn him that he was creating radio interference. So they had an FCC raid. And then he figured out how to deal with the excess energy. Don't try to put it into batteries and blow them up. Blow it out with compressed air and a few other changes to take advantage of that principle of ionizing air, airflow through the system to remove its, or severely reduce its ability to broadcast an electrostatic field. Anywho, so SPICE tries to be imperfect and non-idealistic, but it does so in a contrived manner, and it reflects really our society is contrived as well. A society of electrical engineers, as only one example, but it's very contrived what we do in our society. It's not at all natural. It's so fictional, and it supports the money system, basically. The fiat currency is king, and everything else is subservient to that. Anyway, getting back to Paul Falstad. So he's the pure student who is applying pure electrodynamic theory in its purest form right across the board. So he's got the purest transformer model you can imagine. It is so pure that you can create an over-unity circuit out of that component alone. It'll blow up in your face slowly or quickly depending on how you engineer it, but you don't have to use it. You can use diodes and his capacitors. He, in the software code, he puts a comment to the right in his desktop version to the right of his diodes. Oh, I had to put 1,000 ampere limit here because sometimes diodes act weird. Now he uses a different expression, oscillatory oscillatory behavior of some kind or another, but then he just said weird. He kept it simple. His comments simple. Something else, his lamps are not tungsten filament argon gas lamps, and Edison did not invent that. Irving Langmuir invented that less than a decade after Edison came out with his version, and some guy in England came out with his very similarly, in which you take carbonized plant material, in the Edison's case it was bamboo, as your filament, and you place it in a vacuum. You don't put argon or any other noble gas in there. You put nothing. You suck all the air out of there that you can. And it works fine in a DC power system. In fact, it never burns out. It's when you get it in an AC system, you start having problems. Or it's either that, I'm guessing really, I don't know what the problem is. It's either that or switches. If you don't have any switching, if you never turn the damn thing off, because there are Edison light bulbs still in existence to this day in various fire stations, because they never turn them off. They never have a surge. They never have a change of voltage or current. It's always constant. So I think it's really two conditions. A DC power system, but more importantly than that is to never turn the thing off and on and off and on, because those surges are what shorten the lifespan of those bulbs, unfortunately. And it fries the filament. It just breaks. Otherwise, it would last forever. And that's why Irving Langmuir came up with his tungsten filament argon gas light bulb. And we call it the Edison light bulb, but it's not true. The 10,000 tests of various substances to create a light bulb did not end successfully with Edison's choosing tungsten. That is a lie. And you'll see it on the internet. It's a lie. Or fabrication, if you prefer to call it that. It was carbonized bamboo filament, and in England it was something else. I don't know, from a wood paper pulp product or some another that was carbonized. But in any case, it's the same basis. Carbonized plant material in a vacuum, in a glass bulb, perfect bulb. If you don't give it any surges. Well, switches in Paul Falstad's simulator is also a nice way to go to create overunity. All you have to do is have a timer set to open and close switches at a rapid enough pace, and you'll get a string of surges so compressed that entropy won't have a chance to diminish the power that will accumulate in the form of voltage, firstly, mostly, superseding over current that will be dragged behind as a sidebar. And if you can figure out how to drain the accumulation of voltage without getting in the way of its accumulation, then you've got yourself watts. And I did that with my first pulsing circuit of overunity that naturally pulses, one pulse every 7 seconds, because I raised the time frame up to 1 second in order to get it to pulse. And it literally, the amperage is the same as 10% of our lightning, while the voltage is way beyond any lightning that happens on this planet. So that it's somewhat similar to the output of the San Onofre power plant over here on the coastline in Southern California, but when it used to be in operation, in terms of its amperage, but not in terms of its voltage. But any case. So he's got all kinds of idealisms, the surges of mechanical switching, the surges of diodes doing their switching, because they're switching too, the transformers retaining 100% of their magnetism and not losing it. And if you combine that with one of his capacitors, oh my God, it's so easy to have an overunity circuit. Just short out one end of the transformer, the two coils, with a capacitor, and play around with that. You'll have an overunity in any time, in no time at all. But you can also do it by reducing his time interval. Now, let's get back to the initial reason why I started this recording, my little epiphany. He does not break up the time interval. Spice does. Spice, in its bid to try to be realistic and not be idealistic, will give you time intervals in which each successive time interval is never the same as the last one, unless you specify relative tolerance that forces it to become more periodic in its successive time intervals. But if you just let it go, then it'll contrive a sequence of time intervals in which each successive time interval is not the same as the previous one. And that is to create a condition of impartiality to the observation of the circuit. Because you know that little Heisenberg principle, about physics, about the uncertainty principle, because of our involvement as an observer, that we impact what we look at just by looking at it? Yeah, don't say we don't have mental force, that attitude doesn't give people cancer sometimes. So when you've got a time interval that is periodic and resolute and doesn't change, you have anything but an impartial observer in the form of a simulator software. The simulator software is acting as an observer. Supposedly impartial in the case of spice, contrived to be in weird ways that gives you weird outcomes because of that weird contrivance. But Paul Falstad never does that. He never tries to be weird, which is why he can go to take the liberty of saying, oh, his circuit is weird, or the simulator is weird, or whatever, because he is not. And that's true, he's not. He's being totally holistic in how he applies electrodynamic theory. And so he has a periodicity to his time interval. It's repetitive. You set it and let it go. And it keeps repeating the same time interval. And that injects frequency. No energy, but frequency is a form of energy. It's a form of energy in the sense that it is a potential form of energy, and it is one of the pillars of electrical reactance, which is a form of energy. That's how I get over unity out of my circuits. I pay attention to the principles of electrical reactance. Magnetic reactance, I don't know anything about it, so I won't even go any further. But the principles of electrical reactance are three with a sort of consequential fourth pillar. The three are, well, there are two of them that are standard: capacitive reactance and inductive reactance, resulting from the various impedances of inductors and capacitances. But you've also got both of those within a framework of time, namely the duration of periodicity. Now, I don't mean the duration of a single period, which is unfortunately artificial intelligence online thinks that's what I meant when I used the term duration. So I'm going to have to think of a different term instead of duration. I was trying to be general, and they went and specified what type of duration. Oh, the duration of a period. No, the duration of multiple periods or one period. I didn't specify. I didn't think it would misinterpret, but it does, unfortunately. Some of the AIs online. So I'm going to have to be more specific and long-winded in order to be articulate. But the periodicity of frequency over a span of time, giving us a duration. Yeah, some over unity circuit designs, I have to wait 10 million seconds, which is a couple thousand years, for it to exhibit over unity. But it happens. Excuse me, if you wait long enough. But then I know I got something, because all I have to do is tweak the parameters of capacitances and inductances and possibly frequencies in order to get an explosive hyperbolic rise of power within nanoseconds instead of 10 million seconds. It's hard to get it in between. It's usually the two extremes, but that's microcap for you. In Paul Falstad's case, all you have to do is reduce it less than 1 microsecond of time interval, or go down to the slowest speed. The minute you go from 2 picoseconds to 1 picosecond, all of a sudden your over unity baby comes alive and starts to accumulate power. It doesn't blow up instantaneously. I've done circuits in his simulator that blow up instantaneously. But I keep reducing the time interval, and I can't find when it slowly accumulates power, because it keeps instantaneously blowing up no matter what the time interval. But in terms of this Eric Dollard model that I did in the cell phone app, it depended on my resistances that I put in between my components. If it was 1 ohm, all I had to do was go below 1 microsecond. But if I raised the resistances to 1 giga ohm of resistance for each of those resistors, then I had to go down to 1 picosecond, and it immediately started to explode in its, it explosively accumulate power, let's put it that way, so that within a very short duration of my time, it reached its limit and told you it can't compute the circuit anymore. It can't calculate the circuit. There's a different warning in the cell phone app. It doesn't say nan/infinite matrix anymore. It says convergence error or something, which you can get sometimes in any simulator, Spicer or Falstad. Sometimes you get convergence error messages, sometimes you get singular matrix error messages. Regardless, it amounts to the same thing, because the funny thing about overunity and free energy topology is the symmetry involved. My best circuits are always symmetrical in their layout. They don't subscribe to any kind of contrivance such as rapid mechanical switching. It's simply the layout of the components are totally symmetrical. You can draw a line down the middle because there is a middle, and everything just reflects on the other side, a mirror image of what's on the other side. And it's that symmetry that drives matrix algebra nuts. And that's why I'm so sorry that all the simulators use matrix algebra as a shortcut to calculating the results. It's a big mistake if you're designing the software to host over unity circuits, but nobody does that. They don't expect you to. And that's why they put it in all the simulators, and that's why it's a nightmare. Because you can have convergence errors long before you get anywhere, before you accumulate anything. It starts out and immediately stops. And you look at all the components and say, there's no energy there. What happened? Because matrix algebra saw what you were doing and did not like it, and did not allow you to go any further. So I've had to avoid circuits that has that problem. Doesn't mean they're not over unity. Doesn't mean they don't give you free energy, but it just means I can't simulate it. If I can't simulate it, I can't develop it. So what's the point, right? So I really have a big problem with that. But no, round-off error is not the problem. It's matrix algebra and these other things keep periodicity to a time interval. We're injecting a frequency, which means we're injecting energy even though there's no energy per se, kinetically speaking, but there is energy that we are injecting, and we're no longer an impartial observer. We are an involved participant when we have a frequency that's of time intervals that are periodic, and now we've got a stable input of potential, not kinetic, but potential energy. Doesn't matter. It doesn't give a hoot whether it's potential or kinetic. It's going to contribute to the overall energy of the system. That's why I liken electrical reactance to be the cup and amps and volts to be the sugar. And when you ask for a cup of sugar from your neighbor, you're not just asking for the sugar. You don't want him to pour sugar all over you. You would like it in a container, and so he gives it to you in a cup. And when it comes to electrodynamics, the oddity of it all is the cup can become the sugar, and the sugar can become the cup. They are morphable one into the other, translatable, transducible, however you want to call it. And that's the magic of free energy, is to recognize that the cup can become the sugar and the sugar can become the cup, because it does make a difference what cup you put the sugar into. It makes all the difference in the world. And that's why you have to consider the cup as a form of sugar, even though it's still a cup and the sugar's still sugar. But for all intents and purposes, the cup becomes sugar and the sugar becomes cup in a metaphorical sense. But in actuality, no, the cup is a cup and the sugar is the sugar. But it's not so cut and dry like that in the realm of electrodynamics. It's a gray zone in which how much of the cup is contributing itself as sugar to the sugar inside of it, and how much of the sugar inside of the cup is contributing to the structure of the container, the cup that surrounds it. You can't say that there's no bleed over anymore, like we say with sugar and a cup. With electrodynamics, it's mostly gray as to distinguishing between the two, the properties of the two. It's mostly gray. There's no black and white whatsoever. In fact, there is no black and white. But it's an artificial contrivance to say that it is and to make it, to compel it to be black and white. And that's the artificiality of our world. And it's going to break down in so many different ways. All the different contrivances are going to break down. Not just this focused topic of so-called free energy, free work, call it what you like. I really don't give a shit. It's so arbitrary to try to be vernacularly correct. I know I try to be, but at the moment, I don't give a shit. It doesn't matter what we call it. It's contrived to try to be correct in your usage of terms. Like I won't say who, because it's not a sin to be correct with our word usage. It's just a waste of time. You're not saving anyone's butt, because with imaginary power, it doesn't matter anymore whether it's free energy or free work from limited energy. It doesn't matter, because we're not restricting ourselves to recycling kinetic energy anymore. When you've got imaginary power, this is where the cup becomes the sugar and the sugar becomes the cup, and there's no longer any distinction between the two. When you're dealing with pure imaginary power, in other words, 99.9999999% of your power is imaginary, and only a teensy-weensy little fraction of it is real. Your apparent power is predominantly imaginary. You've got yourself, the cup becomes the sugar, and the sugar becomes the cup. There is no distinction anymore. It's so gray, it's pathetic to call it anything else. So I get impassioned talking about this subject, as you can imagine, because I can see all the contrivances that we have engineered into our scholastic system of training young students of electrical engineering. It's so contrived. But Paul Falstad, bless his heart, he is such a purist, such an idealist in his non-impartiality of circuit software perspective, that you get a whole lesson on electrodynamic theory just by monkeying around with a simulator alone. Even if you never went online to find out answers to your various questions, why is when I do this, that happens, and blah, blah, blah. Even if you never pursued an understanding of what happens when you fool around with a simulator, you will get all the education, hands-on education you need just by playing around with a simulator. I guarantee it. It's remarkable in how it teaches you by experience alone how electrodynamics works in its purest format of theory, with no embellishments or contrivances, other than the ones he did put in, like a limit on the current on his diodes. I'm kind of annoyed with that. But he doesn't really put in any other... so he puts in one contrivance. Okay. So I have to admit, but that's it. That's the only one. There are no others. I mean, he's got the purest... I mean, his light bulbs are Edison light bulbs. They're not Irving Langmuir light bulbs. They contribute current all the time. Any voltage is applied, voltage difference is applied across the terminals of those lamps. But when they light up, white hot, the current they put out, it's remarkable. It makes the it puts spice literally into your over-unity circuit, if I might use the expression, borrow the expression from someone else. It literally spices up the over-unity circuit and makes it come alive with over-unity so quickly. Once those lamps light up white hot, oh my God. And then you know you've got something other than tungsten, because only Edison's does that, not Irving Langmuir, because Irving Langmuir is not an ideal lamp. It's a contrivance. For whatever reason, because AC came into vogue, or because switches, or both, because AC is a kind of form of a switch, just like diodes are a form of switch, AC power is a type of switching action. And so it's really the surges of switching actions in general that caused a problem with the Edison light bulb burning out prematurely, because he didn't expect that. So he gave us an ideal light bulb, and Irving Langmuir gave us the contrivance for our real world, in which change is what you can expect, not constancy. Anyway, yeah, DC is an artificiality. The real world isn't like that at all. But it's idealistic, it's perfect, it's pure. There's nothing obscene about it. And that's why Paul Falstad includes DC transfer capability in his transformers, because in a pure world, that's what your transformers would be capable of doing, is pass DC from one coil to the other and back again. Well, I think I've said enough, but I mean, I'm really trying to give credit where credit is due. I mean, there's nothing wrong with Paul Falstad's simulator. It's beautiful. And his frequency is an injection of power. It's a potential form of injection, but it is an injection of energy, power, whatever the correct term is. I don't know and I don't care. It is an injection of something, and it's very real in the world of his simulator. So his simulator, I mean, unless you're designing a conventional circuit, you can't build any of those. If you try to be unconventional and do a free energy circuit, you're going to find it problematic on how to build it. I still hold that it's possible to build such a thing, or else Nathan Stubblefield would not have been able to run his system on such low voltage that it is an electrostatic system. His whole network, between his power station and his loads, he had a heater in his cabin. He had light outside his cabin, night and day, 24/7. It could be the blackest of night elsewhere, but around his cabin, it was lit up as bright as the noonday sun, and the light was coming from nowhere in particular. He never got electrocuted because he was dealing with low voltage conditions, and it was an electrostatic system, not an electromagnetic. So he wasn't trying to transmit power. There was no power in his system. It was totally voltage oriented, and the only current necessary to keep the system working, to uphold Watt's law, I have to get in the habit now of calling it Watt's law. It's not Ohm's law. Watt's law is the leakage, the current leakage that he built into the loads, the various loads, in order to get the voltage to work. Otherwise, electrostatically, how can you have a system that performs any work if there's no watts there? Got to have some watts, but you don't have to have so much watts that you get billed for it, so many kilowatt hours. It can be so minuscule that you can't even get electrocuted, because the watts come about because of the current. And that's where you get fried, because we fry everything. We fry with so much current, it's no wonder that our bill goes up, and you don't stick your two wet fingers in the electric wall outlet socket. You don't do that unless you want to kill yourself. But in Nathan Stubblefield's system of power transmission, power generation, and power usage, you can't get electrocuted. He had it. His oak tree flourished. The wattage was so nice and low, and naturally using the natural frequencies of the environment, no 60 cycle business that causes people to pass out when they drive on a certain section of the Autobahn in Germany. I learned about this. The story, it was West Germany before the wall came down, the Berlin Wall. But a certain road in the afternoon, when the setting sun cast shadows from a line of trees on the side of the road, across the road, and you drive at a certain speed, drivers have been known to pass out because 60 cycles is the wrong frequency to have. And tremendous current is the wrong amplitude of amperage to have in a electrical network. It's just wrong. It's not with nature. It's against nature. So Nathan Stubblefield, if any thing should be studied, is how he went about doing what he did. Because it's so natural. It's so healthy. You can't get sick from it. I mean, there's one guy who died of leukemia because he played around with magnetism. He had an electromagnetic, a solenoid coil, and he cut out a copper sheet, a hole in it or whatever, and put the disc with the hole in it on top to change the magnetic fields at one of its poles in order to transmute metals, metallic substances, from one metallic substance into another, not gold. But he was doing other stuff, and he ended up giving himself leukemia. And there's all kinds of things that are wrong, that you can do wrong with electricity, and there are all kinds of things that you can do right. As Mitko Gurdjieff pointed out, you can have current leakage alone give you power when you don't create a loop. You don't create a circuit loop to facilitate the return of current and the creation of current in order to return a pathway. Instead, you just have an open circuit. And you design it in such a way to leak current, but not return it to its source or to return it to ground or anything of the sort. You just leak it. And the current leakage is so minuscule that you get power out of it, even though you don't have an appreciable amount of current going on there. You do have some, it's leakage, but it's not contrived artificially or purposely, I should say, intentionally, to encourage current. It provide for it, but not encourage it, but to discourage it. Anywho, so this was all about frequency. The time interval in Paul Fawcett's simulator is an injection of energy, potential form of energy, and that's why it's possible to get over unity just on the basis of the frequency of his time interval alone, if you set up your circuit to take advantage of accumulating power, starting with voltage. And the current leakage will get dragged along and give you power. It may not be much by comparison to the amount of voltage that's going on, but you will get it because there's always some current leakage, even if you don't facilitate the flow of current. Doesn't matter. It'll happen. It'll happen one way or another.